All right. Yeah, I'm Jordan Taylor. I'm being supervised by Ian McCulloch. Welcome to my confirmation talk. I've been working on tensor network entanglement structures. This is a pretty broad topic and I've only got 20 minutes. So today I'll be mainly focusing on isometric tensors, but my thesis might end up being a bit broader than this. Feel free to unmute and ask questions at any time. So first I'll explain tensor networks, then I'll get on to gauge fixing and my work on isometric tensor networks. So we normally represent tensor networks using Penrose notation, where a number is a single blob, a vector is a blob with one leg, a matrix is a blob with two legs, and so on. Set each of these indices, and the tensor gives you a number. For example, setting like I equals 2 on this vector here would return the number at the I equals 2 position. So here are some familiar tensor contractions that you'd already know. So we've got the dot product, which gives you a number, the outer product, which gives you a matrix, the matrix vector product, which gives you a vector, and so on, matrix multiplication. And of course, we can do less familiar contractions as well. So here we've got a contraction over two 3-index tensors, two 3-leg tensors, a blue one and a yellow one, and one vector here in green. So the number in this ij position of this final matrix here, we can see it's going to be a matrix because it's got two 3 legs. The number in the ij position of this matrix will just be the sum of these products. Remember, setting each index in the tensor gives you a number. So for every setting of the indices, this is just 3 numbers multiplied together. And we can have edges connecting more than 2 tensors like this. It just means that those indices are set equal in the sum. Here's an example of a tensor network being contracted. These contractions can be done in any order. Some orders will be more computationally difficult than others, but this won't affect the final result, which in this case is just a 4-leg tensor. The history of tensor networks is a tale of like convergent evolution and cross-pollination. Many of these methods came from condensed matter, such as like transfer matrices in the 40s or DMRG in the 90s. But these were largely limited to 1D quantum or 2D classical systems. On the other hand, general tensor networks were first developed in the 70s when Roger Penrose attempted to build spacetime out of spin networks. This kind of work went on to inspire loop quantum gravity. Penrose's notation was picked up again by the condensed matter community in the 2000s, where it was used to clarify and generalize their methods. And then since 2012, it's come back again to influence quantum gravity, string theory, and black holes, these condensed matter algorithms and techniques. Another independent genesis of tensor networks probably came in the 80s with the development of quantum circuit diagrams, which are tensor networks. The best algorithms for simulating large quantum computers today use tensor network methods, and there's a lot of cross-pollination between fields here too. More recently, tensor networks have also been applied to quantum chemistry, data compression, and machine learning with great success. I'll focus on the context of quantum condensed matter, but my work really applies to any tensor network. So the quantum state of n particles can be written in this way. Hi, Karen. The quantum state of n particles can be written in this way, where C is a tensor with n legs. The number of elements in a tensor grow exponentially with the number of legs, so storing all of the elements in C, this wave function, becomes impossible very quickly. So tensor networks try to solve this problem by decomposing this single huge tensor as a tensor network containing many small tensors and only polynomially many parameters. So working with tensor networks often goes something like this, at least for condensed matter. You start in some state up here. Perhaps this state just represents a lattice of quantum spins. Initially, the state might be just a list of vectors like it is here with no entanglement, a tensor product state. Then various methods can be used to optimize or time evolve the state. So depending on the method, this could give you a 2-dimensional tensor network like this, or a 1-dimensional tree tensor network like this. These two represent the same state, but the 2-dimensional tensor network, for example, might be easy to store, would require less memory, but the 1-dimensional tensor network might be easier to contract. It just depends on the application. So finally, you might want to calculate something. So here we're calculating the energy. by representing this Hamiltonian as a tensor network with these gray tensors, and then sandwiching that between this psi and its conjugate. And then contracting this tensor network just gives you one number, the energy. You can do similar contractions for any observable in your quantum system, or even just perfect sampling from the distribution of your states. So what makes tensor networks useful? Well, they have many great algorithms for optimization and contraction, especially in 1D. As we've already shown, they give you an exponential reduction in the memory compared to storing a general quantum state. But what's the trade-off? Well, they're entanglement limited. They support a tunable amount of local entanglement based on the dimensions of interior indices. Effectively, they lie in this small corner of the general exponentially large Hilbert space, but it's a relevant corner. It's proven that all local 1D Hamiltonians with a ground state energy gap have a 1D tensor network description. So in one dimension at least, these bubbles basically fully overlap. Similar conjectures exist for 2D and beyond. In essence, the relevant parameter for an efficient tensor network representation is entanglement. Before I get to entanglement, I'd like to explain isometric tensors. So isometries are length-preserving maps under some grouping of their legs. I represent them as triangles pointing from their larger dimensions to their smaller dimensions. But the dimensions can be equal, in which case these are unitary maps. Isometries are invertible just by contracting their conjugate along their long edge. So here, contracting A dagger with A just gives you the identity. A useful application of isometries is in the singular value decomposition, or the SVD.
Jordan, I have a question. What was the other picture on the previous slide?
This one? This is also an example of
can you explain that one, please?
So this is an example of two isometric tensors being contracted to an identity. In tensor network diagrams, you're allowed to bend things however you like. So this is really just equivalent to the last.
Two legs sticking from the same point. What does that mean? It's just
yeah. So this is
two different legs. You just put them together.
Yeah, you can just like you can flatten a matrix into a vector. You can flatten an order 4 tensor into a matrix, or any order tensor into a matrix. So B here would just be like a unitary matrix when you flatten these dimensions. But
then
represented pictorially, it's like
what it means on what did you get on the right hand side? What are those?
So this is like the identity in these different subspaces.
Identity.
It's not too important. Really, it's just that isometric tensors contract with their own conjugate to the identity, and the identity is just a line in tensor network diagrams.
Well, if you are saying it's not relevant, it's okay. You can keep moving. It was just from your report. I also couldn't quite get what are these. The meaning of these things and what are they doing? What are they in the report? So please keep going.
Of this later when I come back to the 1D canonical form.
Okay.
So yeah, isometries are used in the singular value decomposition, which lets you decompose a matrix as an isometry, a vector of the singular values, and another isometry. You might have seen this before where this is a diagonal matrix in the middle, but yeah, I like to keep these singular values as a vector. This is great because this decomposition always exists for any matrix X, and it's basically unique up to degeneracies in this spectrum of singular values, these lambdas. So the SVD is useful for defining entanglement in a tensor network. So you can start with some tensor network state. Here it's just a dense tensor, and you can like split it into two regions with the SVD. Here the legs in A and the legs in B, and you split them from A to B with the singular value decomposition. And then you can define entanglement just in terms of these singular values. If there are more large singular values, then the entanglement is higher. The required dimension of this interior bond here is just the number of non-zero singular values. So bond dimension is tied to entanglement. And for those of you more comfortable with density matrices, you can also define entanglement by taking a trace over one subsystem in your reduced density matrix. Then your singular values are already squared. So like I said, a larger bond dimension means that more entanglement can be supported. So the maximum entanglement which can exist across a cut in a tensor network is determined by the product of bond dimensions across the cut. So we can imagine grouping these sites and taking an SVD from these to the other sites, or in a 2D tensor network doing the same thing. And then this interior bond here, which supports the singular values, is just the product of these red bonds. So that's the maximum entanglement between two subgroups in a tensor network. But of course, that maximum is not always reached. The total entanglement is not always something like the sum of the entanglements across each bond. It can cancel out. This is related to the problem of gauge freedom and spurious internal entanglement. So here's a simple kind of example of how gauge freedom can allow spurious internal entanglement, specifically non-local gauge freedom here. So we'll start with a non-entangled tensor network. Here it's just 3 sites. Then we'll multiply in this separate tensor network, which just contracts to the number 1. So multiplying in 1 doesn't change anything. So this is just a gauge transformation since nothing physical has changed about the state. But now when you look at these tensors individually, they may appear to have entanglement between their virtual degrees of freedom. It's just that this virtual degrees of freedom entanglement cancels out when you contract the network or do physical calculations. This is just a simple example. There are a whole lot of ways that this kind of spurious internal entanglement can develop if gauge freedom is allowed. And in some cases, it can exponentially slow down calculations. So it's useful to have some sort of canonical way of fixing the gauge in a tensor network. If the tensor network has no loops, then this is fairly straightforward. To gauge fix a 1D state or a state with no loops, you can just apply the SVD repeatedly, for example. So here we'll start with these tensors on the edges, apply the SVD, and now contract these into their adjacent tensors. And now we're left with an isometry here in this tensor, and we can do the same thing again. SVD, contract with these tensors, SVD, and then contract those tensors. And now we're left with what's called this isometric canonical form, because each tensor here is an isometry from its physical indices and these virtual indices pointing towards this orthogonality center here. This 1D isometric canonical form is great because it removes spurious entanglement and it helps numerical stability. It makes local truncations globally optimal, which is part of the success of the DMRG algorithm, if you've heard of that. It allows all symmetries to be characterized just in terms of local gauges. So it's useful for a theoretical tool as well. And it greatly simplifies the optimization and calculation of local expectation values. For example, here we're calculating the norm of this state, but this just simplifies to this trivial kind of contraction here, because remember, contracting an isometry with its complex conjugate just gives you the identity. So you're just left with a whole bunch of identities here, which is this. The same thing happens when you just calculate local expectation values. For example, if you put a local operators in here, then you wouldn't have to care about anything further away from the orthogonality center than the local operators. So the problem of gauge fixing becomes much harder for tensor networks with loops.
Jordan,
Yep.
What does it mean, tensor network without loops?
This is an example. Well, I'll go back, I guess, to the first slides. I mean, all of these tensor networks have loops. Anything that's not one-dimensional or like a tree has loops. So here, this doesn't have loops. This doesn't have loops, but these two do have loops.
Oh, that means you can make a closed loop by connecting any tensor local tensors. Okay.
Yeah, there are closed loop paths in the tensor network.
Okay, thank you.
And that really complicates gauge fixing these tensor networks. So methods of gauge fixing loopy tensor networks either give up on some useful properties of the one-dimensional canonical form, for example, with this weighted trace gauge introduced by Glenn Evenbley in 2018, or otherwise hopefully keep some useful properties of the 1D canonical form, but only by imposing special restrictions on the tensors. for example, by requiring that they're isometric. And this might perhaps come at the cost of limiting the types of states which can be represented. So we have this kind of general method, but might not be as useful as the 1D form, or this restricted method, which hopefully is as useful as the 1D form, but might not be able to represent anything a general tensor network can. So first I'll talk about this first option, the weighted trace gauge. So here we've got a tensor network, and we've singled out one bond, sigma AB. Now contract that tensor network with its own conjugate apart from these two bonds, and we're left with just this single tensor, and these are the two bonds, the sigma and the sigma. Now just consider this tensor on its own. This tensor is called the environment of this bond. It has 4 legs. The weighted trace gauge occurs when you enforce the dominant eigenvectors of the environment to be identities. And you enforce this for all of the bonds. So here, by eigenvector, I mean you have a tensor here which contracts with this environment to give something proportional to itself. And if you enforce that this tensor is the identity, well, the dominant eigenvector here is the identity, then you're in the weighted trace gauge if you do that for every bond on the left and the right of this environment. This gauge was introduced by Glenn Evenbley in 2018, like I said, and it's probably the most comprehensive method of gauge fixing so far. It's a natural choice because it reduces to the usual isometric form if there are no loops, and practically any tensor network can be put into this form. But spurious internal entanglement is still possible, and local truncations may not be globally optimal. And in general, it offers no shortcut to calculating local expectation values. Any questions? This is a bit technical, the weighted trace gauge, but we won't need much of this. Mainly what we'll need is what's called the cycle entropy, which Glenn Evenbley introduced in the same paper. It also uses this environment tensor here, which is, just remember, contracting everything in a tensor network contracted with itself, apart from one specific bond that you care about. So let's consider all eigenvalues of this bond environment, not just the dominant one. And we can define an entropy of this spectrum of eigenvalues. This entropy is called the cycle entropy, and it quantifies the amount of spurious internal entanglement through that bond. So this gives you a measure of actually how much spurious internal entanglement you have in a tensor network. And another property of it is local truncations are only globally optimal in the weighted trace gauge if cycle entropy is 0. So this is kind of, he gave a gauge and it's not always the best. It has these negative properties, but at least you can quantify these negative properties. Evenbley also gave a costly iterative method of reducing the cycle entropy, but the convergence of that seems slow, and it would be good to have a form which you can put a tensor network in which guarantees no cycle entropy. I'll come back to cycle entropy later, but first I'll talk about the other main option of gauge fixing, which is just to give up on some generality of your tensor network and restrict the tensors to be isometric. Isometric tensor networks really started to be investigated last year and maybe in 2019 in a general way. They make it easy to calculate local expectation values, and they can represent non-trivial states like string nets, which have topological order and long-range entanglement. Although there's certainly some difference between isometric tensor networks and general tensor networks, because correlation functions decay exponentially in isometric tensor networks, which is not necessarily true for general tensor networks. But it's still promising that they can represent these non-trivial states. In fact, last year, Sojima et al. Conjectured that all two-dimensional phases with an energy gap and gappable edges have a two-dimensional isometric tensor network representation like this. So here, these are isometric tensors pointing towards some orthogonality center, just like the 1D case. The 1D case is effectively if you ignore everything apart from the middle row of this. Yeah, so they conjecture that all 2D phases with an energy gap and gappable edges have a 2D isometric tensor network representation. That would exclude phases like the integer quantum Hall effect, but it includes a wide variety of other phases, although this conjecture is still unproven. In terms of their practical applicability, it hasn't really been investigated whether they can have spurious entanglement, whether local. You might want to move the feedback. Okay. In terms of their practical applicability, it hasn't really been investigated whether they can have spurious entanglement, whether truncations are globally optimal, local truncations are globally optimal, or which states are practically efficient to simulate. So there are these nice properties of the one-dimensional canonical form which haven't been shown in these higher dimensions yet. So part of my work has been so far in answering these two questions. So in my work so far, I've shown that finite isometric tensor networks have no cycle entropy, so they have no spurious entanglement loops. As a consequence, local truncations in isometric tensor networks are globally optimal. My proof relies on breaking up an isometric tensor network into regions like a light cone. For isometric tensor networks, it's well known that this is more than just an analogy. Time can kind of literally be interpreted like a quantum channel as flowing in the opposite direction to these arrows out from the orthogonality center. So if you consider any bond in this tensor network, here we've just got this dotted bond here. There'll be a group of tensors which point in towards it, like the future events shown here in red, like the future light cone. There'll be a group of tensors which point away from it, like the past events, pointing towards the orthogonality center. And there'll be other tensors which are kind of like space-like separated events, shown in gray. Then contracting these kind of three light cone regions into three tensors, the future always stays isometric. So it's irrelevant kind of when calculating the bond environment. It goes away, and that gives you a trivial eigenspectrum of this bond environment. And that's true for all of these bonds in any dimension isometric tensor network, so long as it has kind of this well-defined orthogonality center and it's finite. So remember, the cycle entropy is defined as the spectrum of this environment tensor, and because this spectrum only has one dominant eigenvalue, then it has no cycle entropy. And so it has no spurious entanglement loops. So I believe I've answered these two questions so far as part of my work, which verifies that many of the useful properties of the 1D isometric canonical form do carry over to higher dimensions. But there are still two useful and perhaps more practical properties of the 1D form which are unanswered. Firstly, in 1D, any tensor network can be efficiently made isometric just through a series of local operations, like I showed you those SVDs along the chain, without increasing the bond dimension. The same is not true in general for loopy tensor networks. So it'd be good to know what types of restrictions this puts on states, which can be practically represented with isometric tensor networks. Secondly, in 1D, the canonical form makes it much easier to classify symmetries just in terms of local gauges. It'd be useful to know if this is still true for loopy tensor networks. Both of these questions depend on efficient local moves for manipulating isometric tensor networks. I'm running quite low on time, so I won't have time to cover most of these in detail. But these local moves, at least introduced by Mike Zelatel last year, involve disentangling. This is where you take a tensor in your tensor network, and well, first you look at it, take the singular value decomposition across some of its legs. And initially you might require a lot of these singular values. You might have a high entanglement, so a large bond might be required in this singular value decomposition. But just by applying an identity here, or an isometry, you can disentangle this tensor to try and reduce the number of singular values you need, or reduce the entanglement across it. And this is used in what's called Moses moves in isometric tensor networks. This is a way of making a tensor network isometric or moving the orthogonality center around an isometric tensor network. It just involves having some tensor in your tensor network, then disentangling it like this, as shown on the last slide, replacing A with a disentangled version of A, and then absorbing this, these tensors into the surrounding tensor network. The downside is that if you can't perfectly disentangle this tensor A, or if it's not fully disentangleable, if it has always some spectrum, some entropy from across this cut, then you're left with an extra bond in your tensor network, which you need to carry around until it can be like compressed or squashed onto your orthogonality center. And also the question of like entanglement path routing is a bit of an issue. So here is a choice about whether this bond is larger or that bond is larger. It's effectively like how much entanglement you send up versus right in your tensor network. So here's an example of how you use these Moses moves to make, you might use these Moses moves to make a tensor network isometric. I won't have time to explain much of this in detail, but here we use a Moses move and we get this extra long-range bond. More Moses moves, more long-range bonds. We shift these bonds up with a singular value decomposition. More Moses moves, more of these bonds. And remember that the memory you need to store these tensors grows exponentially in the number of legs they have. So these long-range bonds are bad news unless they can be compressed. And in general, you can imagine that might not happen until they get right to the orthogonality center. So these extra bonds might build up and exponentially slow down calculations. And it seems to happen in some cases when you just start in a random tensor network. So part of my work so far has also been improving disentangling methods. So far, they just reduce entanglement, not actually required bond dimension. And I've showed cases where current disentangling methods actually do the opposite of what you want. Although they decrease entanglement, they increase your required bond dimension. And finally, another main thing I've found so far is that an algorithm for making small loops isometric like this, where you just have one Moses move to start with and then a bunch of singular value decompositions around the loop. And I found that this is better on all metrics than the traditional method if your loop has less than 10 tensors in it. But that really hasn't answered this question about what states can practically be made isometric with local transformations and what symmetries can be characterized. So I plan to investigate this in the coming months with these uniform two-dimensional isometric tensor networks. So I'll plan to look at the spectrum of these isometric tensor networks, uniform isometric tensor networks, when they can be efficiently made isometric, and look at algorithms for uniform isometric tensor networks, and also try and find tools to characterize the symmetries. I won't have time to get into this fundamental theorem stuff, but this is just saying in general that the symmetries of a one-dimensional isometric tensor network can be characterized just in terms of local gauges. And it'd be interesting to see if that's true in these two-dimensional or higher dimensional tensor networks. All right, so that's my results so far. I've proved that finite isometric tensor networks have no spurious entanglement loops. So isometric tensor network local truncations are globally optimal. I've developed a better way of making small loops isometric. I've constructed cases where current disentangling algorithms do the wrong thing. So that's the year of my thesis so far. And then my remaining questions and my remaining timeline are shown down here. Mainly, what states can be efficiently made isometric and practically using only local transformations and come up with better algorithms to do so? Is there a general fundamental theorem of isometric tensor network symmetries? That's what the theorem that said that one-dimensional isometric tensor networks are just related by local gauge transformations. The symmetries are related by local gauge transformations. Extending that, potentially. Looking for some new ways of disentangling tensors and tensor networks to overcome this problem of current methods. And extensions and applications to actually simulating quantum systems and machine learning and everything else I showed on the application slide potentially. All right, thank you.
Yeah, thanks, Jordan. So any question to Jordan, please unmute your microphone and you can ask question directly. So actually I have a question because you show a lot of, the figures and the diagram. Somehow I got lost, or maybe I'm not an expert. So maybe do you have some kind of simple example to really show how you really analyze your data, or how you do the, the methods? So
yeah, the tensor network contraction or the like optimization methods or something like that.
Any example is good enough at this stage. So just take a very simple example.
Yeah, I mean, the simplest examples, of course, are this just linear algebra, like, the dot product and the outer product and matrix vector product and whatnot. So here we're just summing over I of the product of element 1 times element 1 plus element 2 times element 2, et cetera, et cetera. But general tensor networks, it's really the same. It's the element at the ij position in here is this element times this element times that element summed over all of the internal dimensions.
Jordan, what are you telling is you're just saying the pictorial representation of matrix products operations that we know can be like this, but in practical sense, what is it that you're trying to do?
Well, these are more than just kind of matrix operations. I mean, sure, you can represent all these as matrix operations, I guess. But
and you can draw them using some symbols, etc. We understand that. But
yeah, multilinear operations as well. These higher order tensors are much easier to think about in this way. But really, it's kind of about these isometric tensor networks and what they can represent. It's an interesting question. What phases of quantum phases of matter correspond to these specific types of tensor networks? It's also a way of classifying quantum phases of matter. You can classify these phases as, oh, do they have this isometric tensor network description or not? And also, of course, for practically simulating them and their dynamics as well. I haven't explained any of the algorithms here, of course, like DMRG or time evolving block decimation or anything like that.
Yeah, I kind of like this slide initially.
Mm-hmm.
And I was wondering if you have done any specific, like when you do it's quite, you keep everything quite abstract, irrespective of any model in mind or anything, right? But
yep.
And then if you try to apply that to any particular model, how is that? How you are going to know in advance which one?
Well, I do simulations.
How to decompose, or do you have any specific examples?
Yeah, I mean, that's kind of what the analytical work is trying to do, is, saying what states should have what efficient tensor network descriptions and how and what algorithms. Practically, of course, I simulate these things all the time, just numerically to see, get an idea of what works and what doesn't. For example, you can do the Ising model, or
right,
or Heisenberg, or random Hamiltonians, or even start in a random tensor network state that without any Hamiltonian at all.
Yeah. Okay, thanks.
Thanks.
Any other question?
Yes, Jordan. The ISO tensor that you found has no spurious entanglement is based on this light cone grouping, or isn't it?
Yep.
Is if I just take a general grouping, will I find spurious entanglement?
Spurious internal entanglement is just a property of the bond, basically. So my light cone grouping is just a way of proving that all of these bonds have no spurious internal entanglement going through them. So it's just a proof method. I've used it, this light cone method.
So in principle, I can take any grouping and I'll still find that.
Yeah. So this will just work whenever you don't have these isometric tensors pointing in a loop, basically. So if they all point towards some orthogonality center, and it's a finite isometric tensor network, then it's a loop. this will work. If you have some sort of like closed time like curves in your model, in your like, effectively that's what this would represent if you had isometric tensors pointing a loop, I guess. Just taking this light cone interpretation literally, then this wouldn't work.
Okay.
Right, but once you've chosen that bond there, right, that decomposition into the different groups is unique, right? Because there's a past light cone, there's a future light cone, and then there's like the space light separated.
Right. Okay. Okay.
Jordan, can you go to your summary slide?
Mm-hmm. Summary or remaining questions?
Remaining question. Okay, it's not here, but in your report you were talking about pointwise nonlinearities.
Yeah, that I didn't have time to get into my ideas on applying this to machine learning, but really there are a whole lot of connections between tensor networks and neural networks, and you can use tensor networks for machine learning as well in their own right. So you can represent neural networks as tensor networks effectively plus nonlinearities, and this idea can be applied to, what's that?
Could you just explain physically what you mean by nonlinearities in the tensor network?
Yeah, sure. I mean, let me see. Yeah, this kind of, so just look at this tensor network down here. So we have a vector contracted with a matrix, contracted with a matrix, contracted with a matrix. This is just simple tensor network notation. But this is also a neural network without nonlinearities, if these bias terms are included in these weight vectors here. So this is the normal way that machine learning people would represent a neural network. You've got an input, a vector, and an output, a vector, but you can equally well represent it in tensor network notation like this. The only difference between this tensor network model and the actual models people use for these deep learning models is that they have nonlinearities in them. So after they contract this vector and this matrix into a vector, they apply a pointwise nonlinearity. That means on every element in the vector, they apply a nonlinear function, like an activation function. So this notation kind of just means I contract this vector with this matrix, I get a vector, and then I do a nonlinear function on it. So you got to contract, because of the nonlinearities, it means that you can't just contract these in any order now. You have to contract the vector with the matrix first and then do the nonlinearity. So it's this kind of nonlinear bubbling, because people talk about bubbling when they talk about contraction orders in tensor networks. It's like you draw a series of bubbles to represent how you're going to contract the tensor network. These nonlinearities impose that bubbling. That's why I call it like this nonlinear bubbling.
Okay, thanks.
So you can imagine doing this for any arbitrary tensor network, just having a tensor network and drawing these nonlinear bubbles in it and making it into this nonlinear model. And then you'd ask, well, does entanglement still kind of make sense in these models? And also, you know, how does the geometry of the tensor network model relate to the expressive power and stuff like that? So yeah, this is a dense neural network or a deep neural network. You can also do this for convolutional neural networks. They have, well, specific convolutional neural networks have exact one-to-one mappings between tensor networks as well.
Okay, thanks.
Okay, is any other question? If not, then thanks everyone. And we are going to move to the next phase. So student and advisor is going to stay and the remaining members can leave the room.
Thanks, everyone.